But I'm not sharing, am I? Oh, God. Sorry. We'll restart again. Okay, that's right. Share clip with audio. Start again. Simplest version is something.
I mean, the only thing I'm worried about is me not understanding them. Like, this is a nice problem. I want to understand them.
Morning.
Bar, do you want to ask him?
Professor, I'm not doing so well. I'm having a lot of problem with the homework conceptually.
Okay, so maybe we discuss after the class finishes. And again, you'll have to remind me what it is.
Yeah, I will.
I haven't looked at it for a while.
Today, Professor, we're gonna behave very well. No more questions that lead us astray from the topic.
No, what I've done today, no, the questions will be okay, but today I've prepared lots of short clips, like they're 5 minutes each.
Okay.
So then, there's a natural pause in between them. And today is the last lecture on discretizations of fields, etc. Next week we go into continuum, which is, more legitimate stuff. Next week looks like your other courses. I'm not trying to teach you anything you don't know next week. And
that's a great video.
You're being very kind to Professor, but it's Thursday morning, live from Chicago. Ask me anything. Why don't you people discuss it and I intervene if I need to intervene?
Okay, so first of all, we are giving this I of D that define as this kind of, you have a factor of 1/2 and then you have those Gaussian integrals. And my question, I wasn't quite sure what that the ID represent. So I thought it would be like the area in D dimensions, area element or something like that, but I wasn't sure. So if anyone has any intuition about what that means.
Yeah, so I actually got a tip from the #1 source of all time, the internet. And what the internet said is that...
You didn't look at Roger Penrose's book that I always ask you to look at? He explains it so clearly in his book, The Reality of Reality, whatever it's called. Go ahead.
Okay. It might have come from that book. Who knows? But
No. But he's just so smart. It's pleasure to read that version. Internet tends to be, dull and stupid, but often correct.
Okay.
In mathematics.
So dull and stupid, but often correct, tells me that this integral is a volume integral over all space. So what I want to do is, when I rewrite it in polar coordinates, I can actually split it up into a radial part, dr, and an angular part, d omega. And it turns out, because the integrand only depends on r, you can actually pull out the d omega part, and that integral over d omega is the surface area.
Yeah, so I understand that, and that's exactly what I did, and then you can solve for the ds for this quantity.
Yeah.
So what does the meaning of ID, Andrew?
What is the meaning? It is the surface area times some factor, I think.
So that's the surface area in D dimensions?
Yeah.
Would that not be the volume?
The meaning is equation 710. Yes.
So I don't understand.
The surface can be expressed. Yeah.
There's also.
Can I say something?
Yeah. Okay.
The way I think of ID personally, often we have to worry about noise, and often it's a good approximation to noise to be a Gaussian noise. So I think of ID as a cloud of points which is concentrated at origin and whose density drops off as you go away from the origin. And when you do this integral, this is the weight, the total weight of the points in a cloud when the density function is given by the Gaussian. That's how I think about it. And, it's more impressive when right now it's isotropic. Now, when we were doing SVD decomposition, we were in ellipsoid. We were not in a sphere because different directions had different prefactors on them or different so-called variances. And, so that's what, for me, this integral means. This integral just says it's the weight of a cloud of noisy points, but it can be related to the surface because it's isotropic.
So it's more of a volume, in between volume and a surface, the ID?
No, I'll say it again. Imagine you have a cloud of points and each one of them weighs a gram and there are 1,000 points. Mm-hmm. So then I can, compute an integral over 1,000 points, but they're distributed with this function. So they're concentrated around origin and their density function drops off as the Gaussian drops off. So then I can replace the sum over the points, each weighing a gram. When there are lots of them, I can replace it by a continuum integral times their density function. And density function is this Gaussian. It says in every direction, for example, in 3 directions for d equals 3, they try to be at the origin, but they're noisy. So they have a density distribution, which is a Gaussian. So then this integral is the total weight of all points in a distribution. I just add them up and divide it. If I knew there was a kilogram of them, I divide by kilogram. But anyway, then it will be 1 because then I'll have some 2 pi's in front, etc. But that's what this integral is. It's a weight.
Okay.
Literally.
Why calculate to the surface d minus 1? I was just
because it's isotropic, so in any direction you look from the origin, the integral is written in Cartesian coordinates, right? Mm-hmm. So integral says I have to look in a direction x1, x2, x3. But the natural coordinates for that problem are polar coordinates because it's isotropic. Wherever I look, I see the same number of points on average, in all directions. So then you rewrite it in polar coordinates, which says important is radius because as I go away from the center, the density decreases. And then I multiply this density function by the surface of the thing, and that's how the surface or volume of the sphere shows up, a surface in this case. Does that make sense to you?
Yeah, can you just repeat the last sentence you made? The last point?
Well, there's a little bit of confusion because you might think of the volume or you might think of the surface. So volume is, sphere has a kilogram points inside of it if they're distributed with the same density every place. Now, every shell has a surface and it's 1 dimension less. So when you go to these polar coordinates, you're really looking at the surfaces. So as you go out, for every radius, there is a surface and the density of points within a little band of that surface is uniform because the thing is isotropic. And then you add up these surfaces and that turns out to be a gamma function. Or Laplace transform or whatever, just an integral. So the natural thing to say is, I'm looking out and I'm trying to see whether the sky is white or black. And that depends on density distribution of stars outside that surface. And, in our situations, the density falls sufficiently away that it looks almost black because I see some close by stuff, but nothing from outside. But basically, when I look from the origin, I only see, angular, angular angle parts of the sphere outside. And in this problem, they're all equivalent. So when you add them up, I get a surface. So that's why SD minus 1 show up. Because, S of D is the volume, but its surface is SD minus 1. They stack up in this way.
Gotcha.
So when I have a sphere, it has a volume which is, I don't know, pi square over 4 or whatever it is. I forget, pi square, something. And, but, its circumference is 2 pi. And, that's also volume, but it's volume of 1 dimension, smallest sphere. So they stack up like this. They stack up using combinatorials or gamma functions.
So I need to verify this, but the volume isn't the volume basically you do the integral in polar coordinates, but you integrate from 0 to 1 for the radial coordinate, and you don't have the Gaussian weighting, right?
Yeah. So volume is when you have uniform density. So you're on planet Earth, and there is no pressure. So surface and all the way to the center, it's the same density. It's a droplet of uniform density that sits in a vacuum once you cross the border. So that will be the volume of a sphere.
However, the Jacobian we use is actually for d dimensions r to the d minus 1 d omega dr. So that's different. But otherwise, there's no weighting.
Yeah, so what happens is that the uniform, if you do the atmospheric physics or if you do the, for example, seismography, heliography, which is seismography of the helioscope, you look at oscillations of the sun. It's actually a beautiful system. One measures thousands of eigenmodes of the sun surface oscillating very accurately. So you assume that sun is uniform throughout, then its weight is just the volume of that sphere going to the surface. But when you do a little more careful calculation, you have to account for the getting denser and denser as you go toward the center, but radially isotropic, if you assume that rotation is not important. So then you are adding shells, and you have a radial function that tells you what the density is. And in this particular case with Gaussian, it's so simple, it's just a gamma function or a combinatorial. Now, why do you see factorials in these calculations?
Right.
The most stupid calculation of volume of a sphere is to say, well, it's like a cube. There is a cube, and sphere fits inside. So in my approximation, I come from Kansas, and in my approximation, there is no pi. Volume of the sphere is just its diameter to the number of dimensions. So that would be a totally stupid calculation. Then you say, well, it doesn't look quite right because, it's concentrated and it's empty over there. So let me say that I've approximated by a smaller polygonal volume inside of it. And, when you do that, then you're going from cube to a small part of the cube. And if you count how many these small parts increase larger cubes, you get k factorial. So you get a better calculation. So you can say, I'm from Tennessee, and not a whole hypercube is filled with the sun. It's only, a corner, which is, let's say, a quarter. And my calculation gets not the volume of the hypercube, but it gets volume of the hypercube defined by k factorial. And then comes Gauss and say, but why are you doing cubes? Let's do polygons, etc. And then you, in the limit, you get gamma function, you get correct calculation, and you get pi's.
Okay. I want to ask about the expression for p of theta, because I don't see that it depends on theta, and so that kind of confuses me. So p of theta should depend on theta because, it depends on what angle.
Well, you multiply both sides by delta theta. I canceled the both sides. So p of theta times d theta is a number. It's how much is in the within angular, spherical angle theta. Density times delta theta. And it turns out that's a uniform density. So if you multiply both sides by delta theta, then it says, you're right, it should be delta theta, but the density itself is uniform and it just depends on the ratio of surface to the volume. So it depends on the ratio of two gamma functions.
So the way I was seeing that though, if I thought of it in like 3 dimensions, if you have a sphere, you're thinking of like a ring, right, on the sphere.
Yeah.
And so you have to account for the radius of that ring, because the area of that ring depends on its radius.
Yeah.
If that makes sense.
I was thinking something kind of similar as well. Yeah.
But it turns out that the dimensionally R's have to cancel out. You're only talking about densities,
The thing is, though,
what remains are these gamma functions.
When you do that,
factorials.
You're going to have a sine theta for your radius of the ring, right? There should be some kind of sine theta in there.
No, that went into calculation of the angle because, it's uniform around it. So both sines and cosines, they've gone into the computation of the surface of the sphere. You're right, there's a bunch of cosines and then you multiply it by d of cosine, which is sine, etc. And that's the boring calculation of volume of the sphere. Now, amazing calculation in terms of gamma functions is that just the gamma function.
But isn't what this says, if you have the probability p of theta d theta being a constant, that any angle is equally likely?
Yes, absolutely. So that's why it doesn't depend on the angle. It's isotropy of the, of this sphere. It's isotropic. It's same in all directions.
See, but
Okay.
if you integrate that from 0 to pi, you get 1. You should get 1, right?
No, this is angle in d dimensions. So you have to integrate over all angles in polar coordinates.
So this is a p of
This
as a function of a
theta
solid
is not,
angle,
it's a angle, whatever the correct word is, but it's
right, like
d theta has 2 dimensions when we look out from our sphere. When I look to the Chicago skies, there is an angle left, right, and up and down. So it's 2-dimensional. If I live in 17-dimensional, that d theta is 16-dimensional.
shouldn't there be always one
uniform.
angle that directly connects you on some sort of great circle between the two vectors? That's your theta, right?
But that has as many coordinates you need to specify it in higher dimensions, like Euler angles, on a sphere, there are 3 Euler angles you have to specify to say where you actually are.
So what is theta here?
It's a multidimensional thing. It's a vector.
So I have a question about the isotropic part. So if the whole thing is isotropic, how do we compute the next part, part G?
In this calculation of, the average height of a random graduate student, because of isotropy, you can choose one direction to be direction from which you measure angles. So I take myself to be x-axis. So that removes one of the angles in this calculation. And now you're just computing if on the surface of the sphere on which I sit at the North Pole, if on the surface of this hypersphere, a student is on some meridian, because, from me, all the, not meridian, all meridians look the same because there is no preference between United States and Russia, whatever. As I look from the North Pole, everybody looks, but the students are further on me depending on what parallel they sit, what circle they sit. So now what I have to do is I have to compute, they're equidistributed on a sphere, they're every place, but they sit on little bands for each meridian. So if I'm, at 45 degrees someplace in mid-latitudes, then I have to compute the area of that strip. And it's the area of the strip compared to the area of the whole surface that surprisingly goes to 0, which means that cosine of the angle is 90 degrees, which means that everybody is orthogonal to me. And, if they're orthogonal to me, I can't see them because I can only see things that have components in my direction, right? Projections on it. So it's really, you're computing a little strip around the meridian. It's very counterintuitive because in our mind, and that's why I give you problems like this. In our mind, sphere is a sphere, circle is a circle. A three-dimensional thing is like Earth, so okay, that's a sphere. And it should be like this for every dimension because we have done it for 1 and 2 dimensions, right? But if you think in the likelihood of seeing somebody, this probabilistic thing, suddenly you discover in high dimension, the sphere is really weird. It has, it doesn't look at all like a sphere when you think in terms of probabilities. And if you check this on internet, because internet knows everything, you'll see very pretty pictures when in higher dimensions, if you project it in terms of probabilities of what you see, it looks very bumpy, this sphere, even though we think of it as a sphere. So uniform probability on being on a surface of the sphere divided by the volume sphere is a very non-uniform quantity. It likes to concentrate itself on this ratio goes to 0, which means the projection on my axis. So you're still using uniformity when you're computing this. You don't break it in any way.
Yeah, I understand that, but my question is, in this expression, okay, we obtain that by dividing the surface area
by the volume.
By the volume. So the surface area to the volume is just S of D to S of D plus 1?
Yeah. Well, but, you have to think of strips to compute probability. It has to be, it's not the whole surface, it's a strip on the surface.
But that's what we have the P of theta, D theta, because we're taking a strip.
Yeah. That's why there is this D theta.
Because what I did, I took this expression and divided by D plus 1. So S of D divided by S of D plus 1. And that's gave.
Well, that's just the ratio of surface to the, but that I can't visualize what that ratio means. But this probability can be easily visualized. Planet Earth, their parallels. The only thing that matters for me as I look out from North Pole is what parallel you're on, because there is no dependence meridian, right? And that means that I have to, look at the strip where you are slightly closer to me on a closer parallel or slightly, few meters further away parallel. And now I have to compute probability that you're in that strip and divide it by probability that you are any place. And probability that you're any place, I assume, is uniform because there is no other thing to assume on isotropic planet. But probability on a strip means that, you're on a strip. And the ratio of these two numbers is the cosine of theta.
I don't understand why you would divide a surface area by a volume. That doesn't have the physical meaning that we want. Like we want to. So what I reasoned was sort of like a very hand-wavy inductive argument. In 3 dimensions, you have the like let's say you have 2 vectors, one aligned with z and one at angle theta to it, like a polar angle.
Yeah.
Then you have like calculating the area of the strip. You have the radius of the strip times. So you have basically you're finding the circumference times the width. So rd theta times 2 pi. Well, r is 1. 2 pi happens to be the surface area of a circle, of a unit circle, and so the surface area.
But that's only true in 2 dimensions, right?
Right. So I was generalizing that and saying, well, maybe the pattern is that.
You have the correct formula. It has gamma in it. You don't have to generalize it. You derive the correct formula in any dimension. You have it.
But like, how do I recognize that the 2 pi is in fact gamma and not just a coincidence for 3 dimensions?
Well, if you do this as a data scientist and you don't want to learn complex analysis, everything is written in terms of factorials. So everything is written in terms of integers. And in that case, you just do a few calculations, and their meaning is what I told you. The sphere doesn't fill out the complete hypercube, and it fills out a corner, and that corner can be put in other corners k factorial times. You can convince yourself that much. So that's why factorial shows up. And then, you take a limit, and you get it without any complex analysis, without any saddle points, without any gammas. You get ratios, factorials. At that point, you say, but what happens in higher dimensions because my data set has 2 million elements in it, or, 7 billion if I'm Google. So it's a large dimension. So what happens? And then you look it up and say it's called Stirling formula. So factorial of, 1 million factorial, I can just look up and it says it's e to the e. It's million to the million. So I can compute that number. It's not a big deal. But that was done by saddle point and complex analysis. Now, as an engineer, you just look up, there's some stupid Stirling formula. I don't know where it came from, but it's in the books. Now, here we do it correctly. We do everything exactly, and we don't, we know why we need a Stirling formula. It's a saddle point approximation to these large numbers.
Mm-hmm. But Professor, when we look at this formula we derived here for the P of theta, if we go higher dimension, I understand your reasoning, but if we go to a higher dimension and we use Stirling approximation, this term is going to be d over 2 to the n, and this is d minus 1 over 2 to the n to the same power. So this is diverging, very slowly, but diverging.
No, I think it's the other way around, but, maybe by the way, I make errors. I wrote this.
Nobody
I don't work in a kitchen. I
years.
asked professor to help me, so I wrote this problem set by thinking. And if I've screwed up and the correct formula is a ratio of these two things the other way around, which I agree with you, it looks like it should be d minus 1 upstairs, then you correct me in your solution and say this problem, professor was wrong. The correct formula is d minus 1 over 2 divided by d over 2.
Well,
I don't guarantee anything in my problem sets.
Okay, because
you do the right thing. Don't trust anybody over 30.
I like that.
If you know anything about classical music or about, yeah.
Yeah. So when you're saying to divide the surface area by the volume, you mean the S d minus 1 by the I of d? That's gonna give you the expression? That's the volume element?
No, I of d was just a quick way of computing the surface. I of d is the trick to get a formula for the surface in terms of a gamma function or a factorial. It's just a trick. But, why do we use this trick? Physicists know how to do only three things: Gaussian integrals, integration by parts, and a third thing. So this is the first thing we know how to do. So everything we do, we try to make Gaussian because we know how to compute Gaussian. So that's why it's Gaussian. Now you can interpret it as a weight of a cloud or point, but just a trick to get the surface of a sphere.
Okay, so you're saying just surface over the volume and at d dimensions, that should give me this formula?
No, you have to think about this probability. You have to understand that formula. But meaning of that formula is that you have to compare the area on not the whole surface of the planet, but just the neighborhood of meridian, and you divide it by the whole surface.
But we didn't
And that's a
mention the
probability you are there.